What's going on, guys? In this video we are going to see an example of Laplace transform circuit analysis. In this particular problem we have asked to find out the zeros, poles and the impedance of the given circuit. Here we have the circuit in time domain. First we are going to convert this one into Laplace domain, and we have to know what's going to happen to this inductance and the capacitance when we convert this one into Laplace domain. Okay, now to illustrate this one better, I'm going to draw this new circuit, this Laplace domain circuit, in standard form. I'm going to write the terms in terms of standard form. Okay, let's go ahead and draw this new circuit. This is our Laplace domain circuit, and here we are going to have the same thing. Okay, let's get rid of these things. Here we have three things right here. This resistance will remain the same. When we convert the resistance from time domain to Laplace domain, it's still going to remain the same, so we just put it as R. Okay, then when we convert this inductance from time domain to Laplace domain, that's going to become L times S. That's going to become impedance. Okay, this is our impedance. Then when we convert this capacitance, that's also going to become impedance. The value is going to be, the value of the impedance is going to be 1 over SC. Okay, so for this one we multiply this given inductance value with this S, so that's going to give us the impedance. And for this capacitance we divide, like 1 over S times this capacitance is going to be the impedance for this one. Okay, now we have this one. Now to find the equivalent resistance, we know that when we have resistance in parallel, we find the equivalent resistance by 1 over R equivalent equal to 1 over R1 plus 1 over R2 plus 1 over R3, something like that, right? We do the same thing for impedance. We put 1 over Z equivalent, this is the impedance equivalent, that's going to be equivalent to 1 over R plus 1 over LS plus 1 over 1 over SC. 1 over 1 over SC is same as SC. Okay, now we can take the common denominator. If we take RLS as our common denominator, this is going to become LS, and here we are going to have R. Then we have to multiply this one with RLS. That's going to become R times L times S square C. Okay, so this is what we have for 1 over C equivalents. Our purpose is to find the C equivalents. C equivalents is going to be RLS over these values. This is LS. Let's write this one in decreasing order. Like here we have decreasing degree, like S square, we write the S square first, then S, then after this value. So first we are going to have RLS square C plus LS, then plus R. Okay, it's always keep the first term of this S in as it is, like itself by itself. To get that one, what we can do is we can multiply the top and bottom by 1 over RLC. In that way we will get rid of this RLC with this S square. Okay, so this is going to become 1 over RL. We multiply this one with 1 over RLC, then in the denominator we do the same thing. So this is going to become 1 over, oh, I forgot to copy the S right here. Here we have to have an S, so we multiply this one with 1 over RLC, 1 over RLC, and if you do that we are going to get, let's write the derived equation. If we multiply that, we are going to get Z equivalent is equal to 1 over C times S divided by S square plus 1 over RC times S plus 1 over LC. Okay, so this is our Z equivalence. Now let's go ahead and plug the values, and if you plug the given values for the top, you are going to get 8 times 10 to the power of 7 S. In the denominator we are going to have S square plus 40,000 S plus 2.56 times 10 to the power of 8, and that's it. Now we can factor the denominator. If we do that, this is going to become 8 times 10 to the power of 7 S over S plus 8,000 times S plus 32,000. Okay, this is our factor. Now here we are going to find out the zeros and poles. Zeros are basically when you put the 0 in the numerator, that's going to be the 0. In our case, 0 is going to be S is equal to 0, because if you put the 0 in numerator, that's going to be just 0. Okay, and poles are basically when we put 0 in the denominator, what's going to be the value if you equalize this one to 0. Like s plus 8000, if you equalize this one to 0, what's going to be the s value? That's p1. That's going to be the pole. In our case, this is going to be negative 8k radians per second, and p2 is for this one. That's going to be negative 32k radians per second, and that's how we do this kind of problems. I hope this helps. Thanks for watching.